So back in chapter 5, we talked about how we don't have to visit a star, put a thermometer on a star to know what the star's temperature is. And in that discussion, we kind of said, for instance, we don't need to touch this poker after it's been in the fire for a little bit to know that it's hot. Because what will happen is that this poker will get hot and then it will begin to glow. And we said that a poker like that, as it glows, we could gather that information that it's sending, that light information, that other forms of electromagnetic radiation, like infrared, thermal energy, and we can make a plot of it. And I'm going to show you plots again to remind you what we talked about in chapter 5. And we could understand then from that kind of distribution of energies coming from that poker, we could understand what temperature it is. Or we could just look at it and say, hey, it's glowing, I think it's hot. And so there are two laws of radiation, or thermal radiation, and they go like this. It says basically as you heat up an object, or as an object becomes hotter for whatever reason, it will send more radiation. It gets brighter. And then the other law of radiation is this second one over here, that it will tend to glow the predominant color of the predominant wavelength. I guess it doesn't have to be a color. The predominant wavelength will get shorter and shorter as that object gets hotter. So I switched two slides. So this slide switched with the next slide according to my notes. But do you remember these radiation curves, where we said, again, these are four objects, and we have gathered radiation coming from them at different wavelengths. That's along the x-axis, and along the y-axis we've plotted intensity. And these four different objects, we've got three stars. A hot star is indicated with the blue line, blue curve. Our sun is the yellow curve, and a cooler star is the red curve. And down here we have a cute little human being at 310 Kelvin units. So that's kind of the distribution of energies that are being emitted by those objects. And notice two things. One is the hottest star here has, it's bright. It's just brighter. I mean, at all wavelengths, it's higher on the y-axis. Notice also that it's skewed here. Its peak is over here, actually, in the ultraviolet region of the electromagnetic spectrum. And then compare that to the coolest star. 3000 Kelvin is this temperature, the surface temperature of the star. And notice that it's not as bright. It's less on the y-axis. And notice that its wavelength is shifted longer. It's a red star. And so remember the image of an assortment of stars that we saw a little bit ago. We saw red stars, we saw blue stars, orange stars, and all that sort of thing. So I'm going to play you this animation. I think this did a good job of pointing out those two laws of radiation. So all I'm going to do is I'm going to go ahead and jack up the temperature, and notice what happens to both the intensity and the color. So luminosity is increasing as I increase temperature, and notice the color is also changing. I just think this does a good job. Okay. So as it turns out, our hottest stars tend to be the surface temperatures of not 5,800 Kelvin like our sun, but 50,000 Kelvin. Now remember that although this is the temperature of the surface of the star, the cores of all stars are if they're actively fusing something in their core, the cores are much hotter than that. And the coolest stars are about 3,000 Kelvin. And just to kind of put that in perspective, remember our sun is about 6,000 Kelvin, or the photosphere is about 5,800 Kelvin. So the temperature of an object actually kind of gives you some general information about what's happening on the atomic or the molecular scale. For instance, if something's cold, like 10 Kelvin, and that is really cold. We talked about temperature scales, and remember that the coldest something can get is approaching 0 Kelvin. So 10 Kelvin is really cold. So matter down at that temperature would not have much motion, and it would be stuck together in generally what we call a solid phase. 100 Kelvin or so, you can have matter can be in its liquid phase, and it's still stuck together in perhaps what we call molecules. Get about, let's see, 10 to the third, that's 1,000 Kelvin. And now notice we have matter that has more energy, matter has more movement, and it tends to not be in its liquid phase anymore, but it tends to be in its gaseous phase. We'll jack that up to 10,000 Kelvin, and what we have here is things that used to be stuck together, atoms that used to be stuck together in repeating units we call molecules. Those bonds break, and we tend to have, it's hard for matter to, in general, to stay in its molecular form. It breaks up into its atoms. Well, at this temperature, 10,000 Kelvin, let's see, this is 100,000. Let's see, 10 to the 5th is 100,000. 10 to the 6th is a million Kelvin. So at these last three levels up here are probably more what we talk about when we talk about the temperature of stars. So notice here that as if something's pushing 10 to the 5th or 100,000 Kelvin, now the structure of an atom as we know it changes, in that the electrons become dissociated from the nucleus, and we have basically negative electrons and positively charged nuclei running around in a state that we call plasma. If something gets really hot, then that plasma is what we say fully ionized. So in general, at least these top two, maybe these top three levels are even what we're talking about. And you might remember this image. We kind of took a look at this a few times, where actually this, I believe, is information that our sun is sending us. And if we look, and you know how you can take sunlight and break it up into its colors of the rainbow using a prism. Well, if you were to look closely, you would see actually there are some dark lines, or what we now know are absorption lines, in the information coming from the sun. And that's related to, or we can link that back to the chemical composition of the sun. We can also, if we know what we're looking for, link that to the sun's surface temperature. So in general, we can get what we call stellar spectra, or information from stars, and we can break them into, I believe, 7 different spectral types based upon ultimately that will tell us the surface temperature of the star. And these down here, the O type, B type, A type, F type, G type, K type, and M type, those 7 types, honestly, you're going to want to kind of familiarize yourself with those 7 types of stars. Notice the O is the hottest type of star, the M is the coolest type of star, and Earth is a G type, excuse me, not Earth, our sun is a G type star. All right, so here is a fingerprint from an M type star. Okay, see those lines? And so if we get information from a star and it looks like that, then we know this information out about it. For instance, we know its surface temperature tends to be even cooler than 3,500 Kelvin. Some examples of an M-type star would be Betelgeuse. Hey, that's like in Orion, right? Proxima Centauri. So let's look at the hottest star. An O-type star would look like this. Now notice that it has fewer dark lines, and honestly, as a star gets this hot, one of the reasons we don't see dark lines is related to it's so hot that its electrons can't really transition because that matter is entirely ionized. So these would be our hottest stars. An example of Sticking with Orion, an example of some hot O-type stars would be the stars that make up those 3 stars that make up Orion's belt. Okay, so here we have, we've talked about Arcturus, where you arc to the star called Arcturus from the handle of the Big Dipper. That's a K-type star, and you can kind of see what its fingerprint would look like. A G-type star, an example of a G-type star is the Sun, and you can see what its fingerprint would look like. An F-type, Polaris is an example of an F-type star. An A-type star, the bright star Sirius, the brightest star in the nighttime sky, its fingerprint would look like this. And a B-type star, Rigel is an example of that, and its fingerprint would look like this. Okay, so we can use these spectral, we can use this, these absorption line spectra. And remember that there's a counter emission line spectra. We could use that too to understand what's happening on that star and trace back then not only composition to a certain extent, chemical composition, but also what the surface temperature of that star is. Okay, so I promise you that you'll need to know these spectral types. This is a little slow, isn't it? Okay, so O, B, A, F, G, K, M. So that's from hottest to coolest. There's 7 types. And there's kind of an acronym to help you remember that. O, B, A, fine, guy or girl, kiss me. Okay. This one I'm not so sure about, but another way to remember the order of the types of stars would be only boys accepting feminism get kissed meaningfully. I don't know. But kind of related to that, here are a group of ladies back in, gosh, was this the 1800s maybe? That actually, they're called these are like the little stellar calculators that actually would cull through these spectra that came from these stars and to put them in piles of the O, B, A, F, G, K, M stellar type. So there you go.